Good afternoon. We have Yigit Bulut. Yigit, it's our partner at EYP Mission Critical Facility. Also, it's our CTO. Yigit has over 30 years of project management and electrical engineering design experience. He's recognized as a technical leader and electrical designer for data centers, as well as other mission critical facilities. He's recognized in the industry and by his colleagues as an authority on electrical power distribution system and related engineering applications for data center and other critical facilities. Thank you, Yigit. Yigit, it's here to discuss about our recent launch on sustainability initiatives that we're working here at EYP Mission Critical Facilities. Yigit, what can you tell us about this initiative?
Thank you, David, for the introduction. This initiative is part of our ongoing approach to furthering the data center design environment, the design approaches. EYP Mission Critical Facilities, has a history of being a leader in thought leadership in this space. And back in the day, we started talking about energy efficiency when nobody else was talking about it. We've always had sustainability, even if we didn't necessarily call it that, as part of our sort of primary approach. But I think what's happening now is this broader discussion in the global marketplace, and it's not just in the data center field, right? This is a global issue. As more and more people and more industries get aware of the concerns related to climate change, and as the younger generations become more engaged and more involved in this process, it sort of makes reasonable sense to start looking at data centers and their role in this overall picture, right? Because data centers are, by their nature, large consumers of energy and of resources. And so sustainability at its fundamental level is a question of how well you manage sort of rare resources and how you minimize the unnecessary consumption of resources, right? So what we did was we looked at this, and there's a lot of technologies, there's a lot of discussions. It's a very, very big topic. But what we thought was necessary was really sort of to not necessarily give a one-size-fits-all solution, because that's not possible, right? That's not even a realistic goal. But the idea was to sort of look at this from a framing objective, right? So start looking at it from putting together the bits and the information that's required for our customers to sort of make informed decisions, to look at the ways that they're doing things, and for us to sort of tailor our designs and our approaches to the data center with that particular dimension in mind, right? Sustainability angle. It's difficult because most things that you make a decision about in terms of in the design process and the construction process, right? Usually it's a cost benefit analysis, and the cost benefits are usually quantifiable in some degree, right? Because if you decide to do a particular topology versus another one, what the trade-offs are in reliability, what the efficiency costs, et cetera, are associated with those things. And so you can make a judgment call. The problem, and energy efficiency is like one of those topics, right? Because it's something that you can do. You can figure out how much it's going to cost you to be more efficient, have a lower PUE, for instance. And it's really relatively easy to quantify the payback, and it's a one-on-one, right? Because the more energy efficient you are, the benefits pay, right? So you can figure out, how you're going to get this investment back. There's a return on investment that you can quantify. Sustainability doesn't work that way, right? Because the costs are things that you're incurring. You're doing things differently, and most of the time, the things that you're doing differently to be more sustainable are usually at a premium. They're going to cost you more. Right. The difficulty is that you cannot essentially quantify what the benefit is, because the benefit is not necessarily directly to you as the owner or the constructor or the designer, right? It's a larger distributed benefit. It's a societal benefit. And how do you quantify that? What kind of price tag do you put on it? If I spend $1 million extra on the design of this data center campus, and I'm going to be more sustainable, how do I know what the return is on that, right? And so that's what makes sustainability as an objective a lot harder to deal with, right? Because it's not as easy to quantify. But on the other hand, it's also something that as awareness of the issues of climate change become more front and center, as the younger generations, our kids, their kids start talking about this, and for them, there's more immediacy, right, than it is for us, right? When we were, when I started out in this engineering field 30 years ago, nobody was, we were talking energy codes, we were talking energy efficiency, but nobody was really sort of thinking about it in the same degree of concern, or it was not as widespread a consideration. But for younger kids, the newer generations, this is very front and center, and it's part of their decision-making process. So what we thought we would do was we would start working on a framework, right? This was kind of, it's not necessarily, like I said, a solution, because there is no unique solution to this. But what we wanted to do was we wanted to start looking at a timeline. We will know what we want to try to achieve. We want to try to get to a net near zero carbon footprint, right? And that encompasses not just carbon emissions, right? When we refer to the carbon footprint, we're really talking about all those things that are associated with greenhouse gas emissions. We're talking about the actual carbon, we're talking about sustainability. It's an all-encompassing measure. But what we're trying to get to is a near net zero future, right? And we know that it's nearly impossible to get there right now. But that doesn't mean that there aren't things that we can do in our designs, in our facilities and things today that, one, either provide us a roadmap or an on-ramp to that better future, or two, just improve the way things are right now, right? We can't just basically say, well, I don't really want to be more sustainable because I can't reach that goal until later, and so I'm not going to do nothing. I'm not going to do anything. That's just not a viable alternative. So what we thought we would do is, working with i3, our partners, is to develop sort of we'll start off by taking a look at the technologies, all the component parts, all the things that go into the design of a data center, and start evaluating these in terms of their various aspects, their embodied energy aspect, their immediate emissions aspect, their availability, right? Not all technologies that are really exciting and have some really beneficial attributes are readily available and deployable right now, right? But the whole idea is we want to give our clients essentially a framework, something they can look at that basically says, here's kind of where our current state is. This is where we're at. We want to achieve this, ultimate goal. How can we get there? What are the things that we can do now that are immediate benefit? What are the things we can do now differently, or maybe look at differently, that allow us to have ourselves positioned in the next deployment, the next build out, the next phase of the construction, let's just say if it's a phase construction, to get us closer and closer to that ultimate goal.
So how do they start? If I'm a client, how do I start engaging? Should I be looking for new data centers? Should I be looking for my existing data center? Should I go solar? Should I go to a wind farm or natural gas? How can I start? Where's the beginning of this?
That's a good question, and I think it's a valid one, because I think that what I answer is that if you think about sustainability, let's just talk about that first off. The first goal of sustainability, right, is not to use any additional resources beyond what you really need, right? And so to that extent, if you're an owner operator and you have existing data centers, I think the first thing you really need to look at is reuse, readapt, and modernize your existing facilities, right? Because I think from a core principle of sustainability, to the extent that I don't have to do any new construction, I don't have to, extract any new resources beyond what is minimally necessary, that's a fundamental, win in terms of sustainability, right? Then the next question is, assuming that, I'm looking at my facilities, and obviously there are different, data centers out there with different levels of capability, different age, et cetera. You know, the idea there is, though, you know, look at your portfolio, decide where you can essentially repurpose an existing data center, maybe do an upgrades, you know, modernization that will allow you to essentially get another 5-10 years out of that data center that might be getting to the point of end of life, let's just call it. That, I think, is a fundamental, you know, starting point. Then, you know, as you start looking at, if it turns out that you need to design a new data center, you need to go to a new data center, I think, you know, it's probably not a bad idea to start thinking about, you know, what are my objectives, right, as a corporation? Because you got to kind of set that up to begin with, right? Even when you're looking at your existing facilities, this takes a commitment. This takes, like I was talking about before, because you don't have the quantifiable cost benefit analysis that you can do. It requires some other driving initiative, right? It's whether it's a public image concern, whether it's just, you know, you just basically feel that it's a fundamentally important thing that you need to do as a corporation because of your standing in it. There has to be sort of that decision that you're going to do it. Everybody's going to say that they're going to do it. I mean, there's nobody out there going out there right now saying we don't really care about sustainability. We're going to design and build and everything. Then, you know, we're just going to. That's not realistic. But at the same time, it's one thing to say something, and it's another thing to say, as a corporation, as an entity, we're committed to it, and we're going to look at things. And because it is going to require, looking at things and doing things that are going to have some costs associated with them. And so that's not going to happen until we have that commitment.
So we see many times, and now we're seeing that, and this has been for years, but the seriousness of this started with the 2030 goals that the United Nations provided. So that's it's pretty amazing that now we're seeing, or we're hearing a lot from our industry, the data center industry. Now, one of the things that I see and I hear constantly, it's net zero. That by 2030 we're going to hit net zero, but then you're mentioning near net zero. What is the difference? And you also mentioned embodied energy. Can you give us some thoughts about that?
Sure. Yeah, so I think, you know, net zero is the whole notion of not impacting or essentially adding any contribution to the carbon footprint as associated with the design or construction, the new data center, right? And I think it's a lofty goal. I think that, you know, and it might be a question of, you know, splitting hairs a little bit here, but the way we look at it is, realistically, if you're doing a new data center, you know, the notion that it's going to be net zero, I think is somewhat misleading, because there's going to be an impact to, you know, the construction itself, the work that's going to be done, and you can do it in ways that are less impactful, that are more benign, let's just call it, from an environmental and the carbon footprint point of view. But we think that, you know, because my concern, or our concern is that as people look at this and go, well, really, it's practically impossible to reach net zero, that they're just not going to necessarily, you know, go for it, right? And so what we want to say is, yeah, you know what, we're trying to get to net zero, and any step you make, any incremental improvement you make, approaching that goal is a good thing. You know, and so we can't, like I said earlier, we don't want to be in a position where we just look at this and go, well, that's impossible to achieve, so we're just not going to try, right? I think that's the thing, and I think part of our strategy, or part of our thought process is that we want to make this real, right? We want this to be a real, you know, we want it to be grounded, we want it to be fact-based, we want it to be, implement, you know, something that can be tangible and implementable plan. We don't want this to be a purely abstract approach to things. Right. And so from that point of view, we wanted to say, well, okay, we're going to try to do the best we can to get to near net zero, but we recognize that depending on how you look at the process, from everything of the rare earth materials may be used in certain aspects of the technology, to how you deploy the technology, how you build the technology, how you get it there. When you put all that together, you know, it might turn out that, yeah, in the short term, you are having a carbon impact, but that doesn't mean that you're not getting closer to net zero, right? And that's kind of what we're talking about. And that's also the question of the embodied energy, right? Because this is the whole notion of, as you start looking at everything, you can't just look at it from the point of view of, oh, well, this piece of equipment is more efficient than something else, because there might be some essentially overhead, let's just call it, associated with constructing or building or getting that particular thing to a site, right? And so when you're looking at embodied energy, what you're trying to do is you're trying to look at the cradle to grave. Yeah, so it's this whole notion of, as you look at this carbon footprint equation, you start looking at what does it take to essentially construct or get the raw materials to put into the device that you're going to use, or the method that you're going to use, and sort of take all that into consideration, because, you know, it doesn't really do us any good if, you know, I'm just going to exaggerate, if it takes us, you know, a huge amount of energy, or it's a very, very resource intensive technology to do something that's going to be, you know, going to give us a benefit in the short term, right?
So even solar, that everyone is talking about solar, it does have some carbon footprint that we need to consider in the equation, whether it's the right choice or not. We always need to consider all options are in the table. So in general, embodied energy, would you be able to define it as the carbon life cycle of a project or of a building?
I think so. I mean, I think it's important that as you define some of these terms, that, you know, you would lay out what it is, right? Because even in the embodied energy, you know, when you're talking about that, you still need to sort of have some boundaries, and you need to set sort of the parameters around which you're talking about it, right? And I think the important thing there is, you know, you can ask two people what they think embodied energy is, and they may or may not include certain same aspects of things. The key thing here is like most everything else that you know, as you start discussing it or comparing things, is lay out the parameters. Here's what aspects of embodied energy, or how far we're going to take it and what we're going to look at. We define it, we establish, you know, sort of our parameters for it. Now, if somebody comes along and says, well, you didn't look at this aspect of it, that's fine. You know, if somebody else wants to study a particular aspect of it, that's okay. You know, then nothing precludes it. As long as the decision of how you define it and what you're looking at is rational, and that you can actually do it consistently, and you're not doing things artificially, right? You're not basically, you know, carving out a portion of the you know, the embodied energy equation because it's not particularly favorable to a particular technology. As long as you're doing it, let's say, equitably or fairly and essentially rationally, I think it's okay. We just need to define it. We got to figure out what we're looking at, and that's the premise.
So one of the questions that we're hearing in the market, it's one of the topics that we're hearing. I'm not sure if there are multiple companies daring to do this, but data centers without diesel generators. Mm-hmm. How does that work? What is your thought?
Yeah. So I think one of the interesting things as you look at a data center, right? We talked about the fact that, you know, data centers are energy intensive, you know, facilities by nature. And one of the most critical aspects of a data center, obviously, is its availability, you know, reliability and availability, right? The ability to run the data center, you know, it can't go down. You know, everybody basically has this notion that, you know, any data center can't go down. And so historically what we've done is, you know, we've had to put in standby generators to essentially back up the facility in case the electrical utility failed, right? And historically, this has always been done and is still done to this day using diesel engine generators. And so as you start looking at this whole notion of trying to get to a near carbon net zero future, you know, having a, you know, 2030 3 megawatt diesel generators on your campus, you know, on your building, sort of doesn't go along with that whole approach, right? Because diesel is petrochemical, obviously. It requires a lot of front end processing to basically get raw oil to the point of diesel to begin with. It doesn't burn clean. It has a lot of emissions associated with it that are part of the greenhouse gas contribution aspects of it. And so, diesel engines are not particularly pleasant or applicable to a sustainable future, I guess, is what it comes down to. The challenge is that there's a reason we use diesel engines as opposed to natural gas engines. The fact of the matter is that diesel, as a fuel, let's call it more energy dense, and so a diesel engine is more capable of being able to start quickly, assume load, and essentially be able to be up and running, right? Because that's what matters. The idea is that you have utility failure, that your generator starts and assumes load anywhere from 10 seconds to 30 seconds in. You can put your data center on your generators, right? And that's needed because what you want to do is you want to minimize the amount of time that it takes that you're without power, because you have UPS, you have other sort of systems downstream, presumably, that allows you to ride through that transition period. But you do not necessarily want to be without, let's just call it, input power to the facility for any extended period of time. Now, historically, natural gas engines, and there are a couple of varieties of them, but generally speaking, let's talk about reciprocating natural gas engines first off. The challenge with them is because natural gas is not as energy dense, let's just call it. Natural gas reciprocating engines are not capable of having the same sort of ability to start and assume load as diesel, right? And if 5-10 years ago, if you ask somebody, hey, do you want to use a natural gas generator for backup? They would have said, no way, because there weren't that many options in terms of being able to have a reciprocating natural gas engine that could come anywhere near the ability of a diesel engine generator to start and assume load of any appreciable size. Well, that was 5-10 years ago. Technology and all sorts of engine manufacturers have been working on this issue, and they've started developing now reciprocating natural gas engines that still are not as, let's just call it, agile in terms of being able to start and assume load as a diesel engine generator. But you start looking at it, and this was what we were talking about before, right? It's a question of trade-offs. Natural gas, burns cleaner than diesel. It still has emissions that are greenhouse contributors, right? Gas contributors. That's not, I'm not saying that's the be-all end-all solution, right? But compared to a diesel engine of the same comparable size, it's a cleaner technology. It has less harm. Let's just say it's less harmful. Now, when you start thinking about this and you start thinking about energy storage and the ability to maybe ride through more cost effectively, et cetera, you start thinking about the paradigm of, do I really, can I figure out a way that I can bridge the gap between my loss of utility and starting my generators and assuming full load? What happens if I can look at that and say, well, you know what, I'm okay with this being more than, let's say somewhere between 30 seconds and a minute, because most of the time we have UPS systems that are basically designed with anywhere from 10 to 15, 20 minutes of storage. So why not start looking at how we're doing the distribution, how we're doing energy storage, and start thinking about, well, maybe I put, because the trend has been recently to reduce runtime on UPS by minimizing the batteries, right? And we've been going to shorter and shorter runtimes. But even then, the minimum is just still around 3 or 4 minutes at end of life. So what do we need to do? Is there ways that we can do the design that we can accommodate the sort of the characteristics of a natural gas reciprocating engine? And by doing that, today we start basically taking that step towards that future goal, right? And so it's an incremental improvement over diesel, but it's something that we can look at. Now, you still have other aspects of this that you deal with, the natural gas supply versus, storage, et cetera. It's not without challenges, but again, 5-10 years ago, nobody would have even looked at this seriously. Now it is something that we can start taking a look at and start evaluating, and that's what we're doing. We're looking at it because the other part of this is that there are other technologies such as hydrogen engines, that we can start looking at now. Natural gas engines that are dual fuel that can basically burn a mixture of hydrogen as well as natural gas that might eventually be able to go to pure hydrogen, for instance, which is, depending on how you generate the hydrogen, again, that whole, nothing is ever clean cut and easy, might be an option. So that's why we started looking at these as sort of an on-ramp, if you will. It was kind of like what I mentioned at the beginning, sort of things that we can do today that provide incremental improvement today and allow us to possibly have an on-ramp or some way or a pathway to get to a better implementation sometime later. So that's why we're looking at it.
Now, when you're mentioning this new way of generating power or backup power, are we considering as an option to use, for example, natural gas as a primary source of power, and maybe even off-grid, or even have the utility company as a backup?
Yeah, and I think this is part of the discussion we're hearing a lot of also, as it relates to this notion of the microgrid, right? And a microgrid, there are very technical definitions of what a microgrid is and what it constitutes. But in essence, the principle of a microgrid is you generate the energy that you're going to consume within, let's say a campus, a building, an area, right? So the whole idea is, the classic paradigm is power distribution. Generating stations are hundreds of miles away. They generate the power. Electricity basically goes across transmission grids, goes across hub transmission grids, distribution, and it gets to your data center, and basically you consume it there. The whole idea here is that in a microgrid, what you do is you take that generation component and you bring it to where you're consuming it. A microgrid, by definition, is essentially any, let's just call it block, where the energy consumed and the energy produced essentially happen within close proximity or within one boundary, let's just call it, right? So when you start looking at natural gas as a, let's say, a standby fuel, right, like we were just talking about, and you start thinking about using it instead of diesel, then you start going to sort of the next step that you can start looking at is, well, if I've got a reliable natural gas supply, if I've figured out the sort of the ways to do storage effectively, and this might be something that, that makes sense for me, why not, instead of having standby generators, have essentially my generators be prime producers, essentially run continuously at a certain level to provide a certain level of the energy consumption needs continuously. And for that application, generally speaking, you start looking at turbine generators, natural gas generators versus reciprocating engines. Now, turbines, when, if you look at them, they are basically, they also have constraints in terms of how long it takes for them to be able to start and assume load. And they're not they're not turbine generators you don't want to turn on and off. Those things you want to basically get them up and running, and you want to keep them running as long as possible, not take them down until you need to service, right? That's when they are the most efficient. That's when they're the most make the most sense. So then you start looking at this and going, okay, well, instead of generating, buying power from a utility company who might have let's say a heavy carbon-based generation fuel mix, right? They might be, depending on geography where they're at, if the fuel mix is 75% coal, for instance, in terms of how they're generating their energy, it might make sense from a sustainability point of view to take a look at this and go, well, what happens if I can essentially generate power on site near my data center or my data center campus using natural gas, for instance? Then the benefit there is that I'm offsetting, the losses associated with transmitting that power from there to here, right, hundreds of miles away. And in so doing, I'm also offsetting sort of the impact of that, let's just call it dirty fuel mix of the utility company, right? So it might make sense, but there are trade-offs. I mean, because data center operators, by and large, are in the business of maintaining and operating data centers or data and IT, right? They're not necessarily power producers. So the whole notion of going into power production as part of your business is not an easy thing to undertake. Now, there are ways that you can deal with other parties, third parties that can come in and do this for you, but that is a harder nut to crack. It's not as easy to do, but it is something to look at because there are, again, these wider benefits that can be achieved and that you can get to. I think it's going to take a while for us to get there where there's going to be this idea of everybody doing their own base power generation using natural gas. But I think that it's not something that, I think it's something that's going to happen. It's going to be a period of time. It's going to be a part of this incremental sort of steps of getting there. But it's not something that, easily pencils out right now for a lot of installations. But it is something worth looking at.
When designing, this is really, really good. And I appreciate all this information, Yigit. When designing this new or this offering this type of different options, does it affect from the data center internally, from a UPS? Do you still need a UPS, AC, DC? Does it change anything inside of the data center?
Yeah, I mean, the short answer is not necessarily, but I think that as we start looking at this, I think that needs to be a core part of the discussion, right? Because I think you need part of the discussion needs to be, as I'm looking at, let's consider this. If I'm generating let's just say we're in a microgrid configuration, and I have my base power generation using my turbine generators that are on site, let's just call it for lack of a better word. I have renewables in the form of a solar farm that's basically also part of my energy mix. And I might actually have other sort of energy sources that are all basically interacting within my grid. The question then becomes, how much reliability do I need to have or design at the use endpoint, right? Within the data center, right? Because if you think about it, you have this balance because you can have the most reliable utility company in the world, right? And they could have, very, very reliable, and your feeder could be, 100% underground, dedicated on your own substation, the best you could possibly get. But the reality still exists that if it's, 100 miles away or 10, 20 miles away, there's risk associated with that distribution before it gets to you, right? So regardless of how reliable that source is, you still typically have to make provisions for that reliability at the end use, right? It's this whole notion of dual core load is infinitely better than a single core load because at the point of use, that's where the reliability matters, right? But then you start looking at it and going, okay, well, if I'm generating my own power, if I have control over my own destiny, if generation or base power is on site, how much or what form does that reliability take when we're getting down to the final mile or the IT or the rack level, right? That's a decision that can be looked at closely. Dual core still makes a lot of sense, and because it still gets you the most bang for the buck, so to speak. But then, you start looking at it, well, maybe what I do is instead of having, let's say, I'm just going to exaggerate, a 2N UPS plant, maybe now it does make sense if I only have one side of my cord on UPS and the other side on my utility source, because the utility source is me, right? It's my own generation plant. I have control over it. My risks are limited because I'm walking distance from the plant versus, a mile away, 2 miles, 10, 20 miles away. That can be a decision that you can think about. Now, if you layer, let's say a base load, your renewable plant, plus you have some standby reciprocating engines still, then you start looking at it and going, well, now, yeah, I can probably just go with a 3-minute UPS plant on one cord, let's just say one side, and nothing other than my standby reciprocating generator and my own utility source on the other side of it. Now, you can also layer on this, because whenever you put renewables into a mix, right, in a microgrid or otherwise, by nature, and what everybody sort of argues about with renewables is the fact that it's unpredictable, right? If you have solar, you can pretty much calculate down to the minutes and the kilowatt hours of exactly how much energy you can produce, as long as you've got a typical day with the particular sunshine, right? But that all goes out the window when it's a cloudy, overcast day, right? And so anytime you have renewables, you have to have associated with it storage, energy storage, right? And that's another big piece of this technology puzzle, right? Well, now, if you've got a microgrid where you've got renewables, base power generation, and you've got the associated, let's just call it utility grade or large scale storage of energy, again, this is another part of that mix, right? That storage that you use for that application is different than what you would use for UPS, right? But it still means that you have another means of energy storage, which means that you have another source of ride through. So when you start looking at it that way, you go, okay, yeah, now we've got options. How do we balance, site-wide campus distribution with my renewables, with my base power versus the storage within the data center? And you need to look at all of that and start balancing that out against each other. Easy. I can talk about this all day, but
right. And one thing that you mentioned, it's about solar cannot be always available, especially during winter months or cloudy days. But giving the example, I did not want to bring it up, but since you brought it up, the case of Texas, what do you think is the success? I mean, the things that happened in Texas, I call it the perfect storm, because it was the worst of the worst case scenario. How would this affect when designing using different sustainability methods?
Well, I mean, I think Texas is a case study in what we were just kind of talking about, which is, when you're looking at an energy sort of, and if you consider Texas is a microgrid that happens to be huge, right? The problem or the challenge with Texas is that, unlike the rest of most of the United States, the Texas energy grid does not have interconnection and is not able to work nicely with its neighbors, right? And so when I was kind of joking, because Texas is in essence a microgrid that just happens to be very, very large, and so that was part of their challenge, because when you look at Texas and you had an event that's not something that you can necessarily design for or want to, because it's a very rare event, right? They had, by the virtue of the way that they had their system set up, they had no way to essentially offset a loss of a generating source of significant size, right? And so, unlike what the initial sort of discussions were, with the cause being the windmills going down, which really made no sense. And the issue was a lot of their generation was natural gas based, and it got so cold and they were in such a rare event that they lost their natural gas supply, right? Well, if you boil this down to a smaller entity, let's say our microgrid, much smaller than Texas, right? That by all means, that means that we need to start looking at what are some reasonable safeguards that we need to put in to be able to design our system, to be resilient. And typically that's going to mean that we're going to have probably some interconnection with our neighbors, the utility company at this point, let's just call it, that will allow us that, at a certain level, to be able to get to them when things really go, south, let's just call it, on our site, right? And so the challenge there again is the balance of economically, how much does it make sense for me to have standby power from my neighbor, the utility company, versus how much I'm going to basically generate on site. There's a whole commercial discussion that goes into if I'm generating power on site and I want to be able to interconnect with the utility company, am I going to sell them power if I basically generate more than I can use on site, right? That opens up a whole can of worms. But yeah, I mean, that fundamentally, as you look at this, you need to sort of decide what level of risk, what are my reliability concerns, and how do I mitigate them? And I think at some level, at least initially, you're probably going to have sort of some sort of connection to the outside world, to the utility grid. You do anyways for natural gas supply, unless you're generating natural gas on-prem. But I think it boils down to a decision, like everything else, of what are my risks, what are real. If it's something that happens once every 100 years, do I really need to figure out what it is? And when it happens, how do I respond to it is probably the other part of that. I think that's also a consideration is that you don't necessarily need to design for something that happens very, very rarely. But if it's a possibility, you need to start thinking about, well, if it's not for frost or freeze, what happens if I lose my natural gas supply? Right. What is my response? How do I deal with it? That has to happen.
So the storage is going to be also key. So it's not necessarily also using natural gas as the main source of power, but also storing the natural gas in case of an unexpected event.
Correct. I mean, I think because in the end, like I said, unless you've got natural gas wells on site, you're getting that from a utility anyways, right? It's not electricity that you're not getting natural gas. And so you have to deal with the possibility or the eventuality that supply goes away, right? And that might be storage on site. And right. That's also, again, part of this discussion, like, some of the things that we were looking at in terms of like hydrogen, right? Because if you can generate hydrogen on site, and you can use your renewables to essentially generate the hydrogen, for instance, that also is a consideration, because that's additional fuel that you can generate and store on site versus something you have to get from the outside world, right? So these are all parts of, like I said, there are a lot of technologies, there's a lot of approaches, and it's real easy to get lost in all the things that are going on and that can go into this. The idea here is we're not trying to boil the ocean, right? We need to basically make rational decisions, put out rational sort of approaches to look at things, be able to evaluate it, and then decide what mixture and how it's applicable to this application, to this client, to their objectives.
I would like to thank you. I would stay here for 4 hours or even more. I was enjoying it so much. I hope we do another one of these sessions very soon. Thank you again for your time.
I appreciate it. Thank you.
Thank you.